All right. So, continuing on through chapter 1. First, kick off here. So, find the limit. The limit as x goes to 1 of x to the third minus 1 over x minus 1. Now, first thing we always try is, can we put this straight in? Well, if we put 1 in here, we're going to get 0 on the bottom, so that's bad. So we're going to look for that equivalent equation. So what we're going to do is we're going to factor out the top here. So the limit as x goes to 1 of, well, the bottom's already factored, so it'll stay there. The top is a difference of cubes, so it's going to go to x minus 1, x squared plus x plus 1. Okay. So now we have something to cancel. So now we can do the limit as x approaches 1 of x squared plus x plus 1. Now we can put 1 there and we'll be fine. So 1 squared would be 1 plus, well, 1 plus 1, and we get 3. So 3 would be our limit of this original equation. So when we can't do direct, we'll find an equivalent equation. So factor it out, see if you can reduce some stuff, cancel some stuff out, and then make it work. Now, we're going to be looking at continuity. Continuity means that there are no interruptions in the graph, so no holes, no jumps, no gaps. So it goes straight on through. There's no, like I said, no spot where we skip, where there's not something where it jumps to another one. It's straight on through with our graph. So the three things for continuity are, first, f of c is defined. So what it means is the point will exist. So there can't be a hole there where everything works up into it, but that one point doesn't work. So that point has to exist. Next, the limit has to exist. And lastly, the limit has to equal the point. So point exists, limit exists, point equals limit. So if we get, say, 3 for y at this point, and we do our limit, and that limit equals 3, then the limit and the point has to be the same, which they're both 3, so that works. So say there's going to be points where, hey, the point exists, but yet the limit's going to something else, then it's not continuous. There's a jump there, okay? So point exists, limit exists, point equals the limit. So the official definition here of continuity on an open interval is a function is continuous on an open interval a to b if it is continuous at each point on the interval. A function that is continuous on the entire line from negative infinity to infinity is everywhere continuous. And this is not us. Is everywhere continuous. So think all it's saying is from, if it's continuous on an open interval, there's no gaps, no jumps. It's from this one to this one, smooth line. Smooth curve, I should say. Now, if it's not continuous, then the function is said to have discontinuity at a certain point. So discontinuity means that there is a break, there is an interruption in that graph. So the two types are first removable. So just like doing the limit up top, we could remove what causes the interruption. So that's removable discontinuity. The other one is non-removable discontinuity. So no matter what we do with it, we can't get rid of that spot. So we can't redo the equation and cancel out what causes the issue. The issue stays. So that's non-removable discontinuity. So tell whether each one has which type of discontinuity. So the first one, so I'm going to do A, is going to be non-removable. So 1 over x. We can't have 0 because that'll cause an issue. So there's discontinuity at 0. And there's nothing on top that we can cancel with the bottom, so that's it. Second one, though, B, will be removable. I'll just leave it as that. because this top would factor out to be x plus 1, x minus 1, and so we'd be able to cancel with the bottom, which causes our issue. And so we'd be able to get rid of that discontinuity with b. C, though, well, C, the only thing is we'd have to check and make sure that we have our overlap. So at 0, if we put 0 in here, 0 plus 1 is 1. 0 squared is still 0 plus 1 is 1. So there's not going to be a break. There's not going to be a gap. They're going to be at the same spot. So for C, it's actually continuous everywhere. And if we look at D, sine, there's no place that would cause issues with sine. It's just going to bounce back and forth. So it'll be the same thing. It'll be continuous everywhere on that domain. Now, before, well, okay, I'll wait that. Hold that thought. So we can also have one-sided discontinuity, or one-sided limits. Sorry, one-sided limits. We're going to look at what happens from either side. So remember, in order for the limit to exist, both sides have to go to the same point. If they go to different things, the limit does not exist. But we can still find, well, what is each side going towards? We know they're not going to the same thing, but, well, what does each one do? Well, if we have the little plus on the back side of it, that means from the right side. The little minus means from the left side. So from the right side means from a number bigger, working down towards it, what's it doing? And the left side means from a number smaller, working up to it, what is it going towards? So on this first one, we want to find the limit as we go to -2 from the left side. Well, if we put -2 in here, -2 squared would cause a problem because that'd be 4, and 4 minus 4 is 0. Actually, we'd be all right because square root of 0 is still 0. We can still do this. We just don't want to get a negative. Well, what is it approaching from the left side? So if we're less than that, so say if we're at -2.1, 2.1 squared is going to be a little over 4, and so we're going to subtract more than that, and that will cause us to be an issue. So actually, just looking at my notes, and I'm seeing that I have a different number in there, but yeah. So left side of -2, yeah, it's a less than, so it's a bigger number, so we're subtracting more. So we're going to be less than 0, which is negative, which is going to be an issue. However, if we put -2 in there, we're going to be approaching 0. So we're going to get closer and closer to that point. So that's maybe the point I'm trying to make here. And I had a little brain fart, sorry. So we can't put in a number actually that's less, because we're going to get an imaginary number. But we can still see what we're working towards. We're still working up towards that 0. So we're going to get a smaller number there. And the smaller of a number we get, so the closer and closer we get to -2, the smaller and smaller of a number we are from 4, that we're going to subtract less and less and get closer and closer to 0 is really what it's going towards. And I'm probably making this really confusing, and I'm sorry we're doing that. So why don't we move on to the next one, and maybe I can redeem myself here. So one-side limits is what really are going to help us with step functions. So there are going to be certain functions where, again, we're not going to get an overall limit, but we can still see the one-side limit of what is it doing from each side. So step function here is the greatest integer function. Looks like that, where we have the double brackets on each side. But really what it's saying is the biggest integer not bigger than our number. So if we're at 3.2, the biggest integer would be 3. If we're at 3.8, still 3. But if we get to 4.2, well, now our biggest integer is now 4. So the biggest whole number, positive or negative, that's not bigger than our number. Now, at our certain numbers, so say here at 0 or at 1, at 2, at 3, the one-sided limits are going to go to different things. So this is where our graph looks like this. Okay. So, if we're looking here at 0, from the left side, we're going to be down here at -1. From the right side, we're going to be at 0. So that's more what I'm talking about is what's our y value on either side. So left side, our y value is down here at -1. The right side of that point, we're here at 0. So notice the overall limit would not exist because we're not going to the same thing. Both sides have to go to the same thing. Here, each one-sided limit, though, would exist. It would go to something on the left. It would go to something on the right. So that leads us to that next theorem. Theorem 110, the existence of a limit. In order for a limit to exist, that limit of the function f of x has to approach the same L, basically. So the same limit. So the left-sided limit is the same as what the right-sided limit is in order for the overall limit to exist. Now, another way to look at discontinuity on a closed interval, so from a certain point to another certain point, is we have to have a limit exist on the right side of that point all the way until the left side of the other endpoint. And then we'll be continuous in between. So, same thing if we have a partial open and a partial close sort of thing. Now, if we look at the continuity here of this equation. Well, first off, what's our domain? Well, our domain is going to be from, well, what's the smallest we can put in here? Well, -1, because -1 squared would be 1, and 1 minus 1 is 0, and that's as far as we could go. We have to stay positive from there. Well, what's the biggest we could go? Well, 1, because 1 squared would be 1, and 1 minus 1 is 0 again. And we're going to be continuous on everything in between. Now, a way to check would be if we did the limit as x approaches, say, -1 from the right side. So the closer we get to -1, so the smaller we get with the number. So if we're at, say, -0.9, well, -0.9 squared isn't going to give us 1, and so we're going to be positive here because we're not going to subtract as much as what's there. So that works. This exists. However, it will go towards 0. I totally messed this up. So then we're going to do the limit as we approach 1 from the left side of our function f of x. Well, from the left side, we're building up. So if we're at 0.8, 0.9, when we square it, we're going to be a little shy of 1, which means we're not going to subtract as much as we have, so it's going to be positive, so that works. However, the closer we get towards 1, the less of a difference there is, and so we're going to end up with 0 here. So that's where we're getting those limits. So, some properties of continuity. So, if we take a function and we just multiply it by a number, it's still going to be continuous if it was continuous to start with. If we add two or subtract two functions that were continuous each, the result will also be continuous. Their product, if we take each one that's continuous and multiply them, it'll stay continuous. And if we divide them, it'll still stay continuous everywhere that the originals were. Now, the following types of functions are continuous at every point of their domain. Every point of their domains. So a polynomial function. So any sort of polynomial, if it's a function, it will be continuous everywhere. Rational functions. If we have a function over a function, it's going to be continuous everywhere, except for where q of x will equal 0. So as long as it doesn't, it'll be continuous everywhere inside the domain. Any radical function, as long as it's only the positive root of it, it will be continuous everywhere. And trigonometric functions of sine, cosine, tangent, cosecant, secant, cotangent, you'll be continuous everywhere in its domains of each one of those. So for example, if we had x plus sine of x, it'll be continuous everywhere because x is continuous everywhere, sine is continuous everywhere, so add them together, we'll still continuous everywhere. If I took tangent and times it by 3, still continuous everywhere inside that domain. Here, x squared plus 1 over cosine x. Each of those by themselves would be continuous everywhere in their domain. So together, still continuous. Now, continuity of a composite function. If g is continuous at that certain point and f is continuous everywhere that g creates, I guess you could say it contains, then the composite function given by f of g equals g of x is continuous at that point. So what that's really saying is we have to be continuous at the point we're putting into our function, plus anything that we could get out of the first function would have to be still make the second function work. So as long as that point or whatever we would get out of our first point or first function doesn't cause problems with our second function, it's going to be continuous on that domain, that interval. So as long as f and g satisfy the given conditions, the limit of the function will equal whatever that point is. So still probably a little cloudy or as clear as mud with that. But like what it's saying is if I do, say, f of g of 2, well, it has to, so what it's saying is it has to be continuous at that point in g. And then whatever we could get out of g has to be continuous for the f function. So if we put 2 in for g, whatever we would get out would also have to be continuous for f in order for this to have a limit. So it has to work at that point for the inside function and the overall function, basically. Now, looking at here for which intervals will the function be continuous? So we have tangent of x, we have a piecewise function involving sine of 1 over x and 0, and of x sine of 1 over x and 0. So if we start with a, tangent is going to be continuous everywhere except at, let's see, so x cannot equal pi over 2 plus any multiple of pi from there. So if you would graph this, you would get vertical asymptotes every pi apart from pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, as well as going the other way of negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2. So it'd be continuous everywhere else. For B, so we're looking at, we have a piecewise function going on. So obviously we don't want x to equal 0 because 1 over 0 is bad. Otherwise, sine is continuous everywhere else. But however, our piecewise function says, hey, when it does equal 0, we're just going to get a 0. We're going to switch there. And so that fills that in, making it continuous everywhere. Just read my notes, making sure we're good to go with that. So it would be continuous everywhere else besides when pi over 2 plus plus pi, yep. Now here we would be continuous for b technically from negative pi or negative infinity to 0, union with 0 to infinity. Because x equals 0 causes an issue at 0. For C, well, it'd be the same thing, where it's negative infinity to 0, union with 0 to infinity. Because again, that's going to cause issues. Even though that x times out front would go to 0 and 0 times anything is 0, it's still going to have similar issue of as we get closer and closer to 0, it's going to start oscillating. So we technically won't be able to tell what it's going towards. So it'll still cause an issue there at 0, so it would be everywhere else besides 0. Intermediate value theorem, which is theorem 1.113 or 1.13. F is continuous on a closed interval from a to b, and k is any number between f of a and f of b. There is at least one number in C from a to b such that f of c equals k. So what it's saying is that if we know we're continuous between these 2 points, from A over to B, if we know we're continuous all the way through, and if we know that, say, we have a number between those two A and B, those two endpoints, somewhere along the line there has to be at least one spot where we're going to equal that. So, for example, if we're between the points, let's say 0 and 5. Well, at 0, we would get, say, 2 out for our function. And if we put 5 in there, we're going to get 6 out for our function, just for example. Well, as long as we're between 2 and 6, at some point that number will exist somewhere in between there. So, say 4. There's at least one point in between our two x's of 0 and 4 where we're going to get 4 because we start with 2 and end with 6. So somewhere we have to cross that threshold of 4. Which makes sense. If we're continuous, we don't have any breaks, we don't have any jumps, no gaps. So it has to go straight through, so somewhere it's got to cross it. So, to do the intermediate value theorem, here's what you have to do. You're going to do f of A, f of B, which your endpoints of your interval are A and B. So we're going to find f of 0 and f of 1. So if I put 0 in here, 0 cubed is 0, plus 2 times 0 is 0, minus 1, I'd get a minus 1. If I put 1 in here, 1 cubed is 1, plus 1 times 2, which is 2. 2 and 1 would be 3, minus 1 would be 2. So what that's saying is somewhere in between there has to be a 0. So we have to equal 0 in between. Well, if we're starting at negative and we're going positive, somewhere we have to cross over. So we would say, therefore, so 3 little dots, by IVT, a 0 exists between 0 and 1. So, find the first endpoint, find the second endpoint, show that they're different signs. Then we know there's a 0 exists between 0 and 1 by the IVT, so which is the intermediate value theorem. Now, if we wanted to narrow that down, we could keep doing the intermediate value theorem and get as to where that 0 is. So maybe we go, okay, from 0 to 1, there's a 0. Okay, looks like we're closer to it the smaller we are, so let's go from 0 to 0.5. If it's still in there, then you can narrow down, say, from 0 to 0.25. And you could keep narrowing it until you get to where that 0 is at. However, that is time consuming. It does take a little bit. But that's something you could do. Now, that's it for this lesson. So, questions, comments, concerns, pan me, email me, send me a message on Google Classroom. Remember, you can always pause if you need time to write stuff down. You can always rewind something if you need to hear it again. Otherwise, until next time, we'll talk to you later.